Okay. Oops. For 29.7, let's continue to use a capacitor as our example. So let us have a capacitor in which there's an electric field stored between that. Because there's a charge positive Q on one plate and a charge negative Q on the other plate, which can exist only because there's a change in potential over that plate. Now, to assemble these charges, basically what I have here is an assembly of charges. From what we did at the beginning of chapter 28, that takes work. So, we needed to put energy into this in order to create this in the first place. That means there's energy stored inside of this. If I were to allow this capacitor a chance to connect, if I were to remove this delta V and just connect both sides by, give the charged particles a way to move from one side to the other, then all the excess negative particles over here would move through that path and balance out these positive holes until it would come back to neutral. Because it's not neutral, there must be some work that was done to build that, to construct that as it is, to set that up as it goes. Now, to take an idea of where this comes from, let's look at a tiny differential piece of work done by a bit of charge that moved, by a differential charge moving through a change in potential delta V. And this comes back from, going back and forth between the energy concept of the electric potential energy and electric potential. Because I need to get into energy to find out how much energy is stored here, I must move back and do that case. Okay. From, for a capacitor, the charge, actually let's put this here, the charge on a capacitor is equal to the capacitance times delta V. Now, the capacitance is constant. You'll recall that it depends on the geometry of the system. We looked at a very straightforward parallel plate case. Even if I made a more complicated case, it's the geometry, it's the physical existence of the capacitor, how that is, that defines this case. So, let us move on from there, and therefore a differential piece dq, I could write that, or actually, let's write then that, a differential change in the electric potential. So let me write then that this as, charge Q moved over a tiny different change of potential. And let me use this to write the change of potential energy as being Q times delta V, which is dQ over C. So if I want to find out the total amount of energy stored in that system, I integrate from 0 to capital Q over the entire charge of Q dQ over C, which is 1/2 capital Q squared over C divided, or minus 0 squared over c, or 1/2 q squared over c. So, the energy stored on the capacitor is 1/2 q squared over c, and because I've got the relationship q is equal to c delta v, I can write that as 1/2 c times the change in potential squared, or let's see, that's replacing q with CV. If I replace c with q over delta v, then I have 1/2 q delta v. All three of these representations represent the energy stored on the capacitor. Now, where is that energy stored? That energy is stored in the space between the capacitance. So, let's look then at the energy density, which is, which way shall we go? Let's look at it as 1/2 the capacitance times delta V squared divided by the volume of the area, A times D, if this has cross-sectional area A and separation D, and I've got the capacitance as epsilon naught A over D times delta V squared divided by, oh, whoops. Yeah, we represent that. And we can also get rid of delta V. 1/2, okay. The A cancels out. Epsilon naught over D squared. Well, delta V is just, the change in potential is just ED. So that's the electric field times the separation squared, or the energy stored in a region of space is equal to 1/2 epsilon times the electric field in that space squared. We don't have to know the geometry. We just know the electric field. We can find the energy stored in that space. Now, this is for open space. Let's look at a different example when I've got something in between there.